Hi, I'm Shane McGrath. I have over 10 years experience in the data analytics space and degrees in economics, maths, and statistics. Here I'm going to talk about the geometry of concepts, a paper about um, um, sparse autoencoders feature structure. So this is similar to the learning by reconstruction, and this paper doesn't go into as much depth as the learning by reconstruction, and really is highlighting some interesting or intriguing to some um, properties that these sparse encoders contain. So it was kind of a question that I certainly um, was on my mind after doing after researching this sort of geometric algebraic neural intelligence. There is the geometric intelligence just for like objects that have geometrical properties anyway, such visual geometrical properties such as like the uh, a book or a mug or a mug, not a, or the glasses, or do concepts themselves have these sort of geometric properties? So this paper kind of indicates that concepts do have these sort of geometric properties, and again, because they're geometric, they can be linked to other mathematical properties such as groups, essentially. So the groups are the kind of underlying mathematical structure that can kind of be linked to a lot of things seemingly. I posted a video about the Fermat's last theorem, which kind of talks about how mathematicians prove this sort of stuff. Um, uh, Usually with lots of paper and over many years. Um, so sparse encoders. So the paper says that there's various different levels of sparse encoders. There's the atomic small scale crystals whose faces can be parallelograms or trapezoids. Then there's kind of bigger kind of brain intermediate structures with significant spatial modality. So this would be the kind of mathematical coding kind of structures. Um, so the analog here is kind of like a brain like lobe. Like as I've kind of mentioned before, the locality of data seemingly is important, sharing mutual information. The previous video I talked about this kind of method for training data. So this is more a method for data structure. However, that paper made the point that a lot of these sort of information structures don't have like get the standard statistical distributions. So seemingly it's more of these sort of geometric group structures. And then finally, a galaxy scale, large scale structure of a feature point cloud that is not isotropic, but instead has a power law of eigenvalues with steepest slope in the layer. Cool. A sparse autoencoder is a type of neural network. So this is the neural network that learns efficient representations of data from its hidden layers, which are made to be sparse. So the crucial point here is that the hidden layers remove a lot of the data and allow for the neural network to isolate crucially. I was kind of saying this in the previous video, the essence of a concept, but something like that, or some sort of geometric structure that the model is able to pick up on. and this means that only a small fraction of the neurons should be active at a given stage. So, interestingly enough, it allows the model to isolate different properties, and presumably this can be used for combining different concepts together. Again, this is a positive note about the geometric knowledge theory, I suppose. So here is what they look like. So input layer, hidden layer feature, and then output layer feature. So kind of what your neural network it looks like, as opposed to it has this sort of autoencoder feature, which is um, it has some sort of learning training property, which is almost like a neural network of its own from what I gather. So the SAS feature structures. So there seems to be a few interesting papers on this. So I'll definitely be do review more of them in these sorts of videos. Sparse autoencoders have relatively recently garnered attention as an approach for discovering interpretable language model features without supervision. The learning by reconstruction, unstructured learning process, where you use the language model itself to learn the features. It's essentially seemingly by forcing sparsity on the hidden layers. And then function vectors were embedding models. So the function vector is crucial to this um, sparse encoder, and then the word embedding models. So this is what the atomic scale looks like. They use PCAs, LDAs, so these are statistical techniques to reduce noise, essentially. But crucially, they work off things called eigenvalues. So these eigenvalues, again, have these Fourier series properties, which again then links back to these sort of algebraic groups. Presumably, this is what allows the network to construct these concepts, is what I'm hypothesizing here. So this is kind of what these lobes look like. There's English text, code, and math, and then the features of the point cloud identified fine-tuned together within documents, and then co-located in frontal lobes. A two-lobe partition was used to break the point cloud. So these point clouds is what the Sparse encoder constructs, from what I gather, into equal parts, and then code and document. A tree lobe is seen. So these are the lobes, the information lobes that can be compared to um, let's say mammalian or human or animal information structures essentially. Yeah, those are the kind of low-best ones, and then here's the kind of brain scale, mesoscale, modular structure. We zoom out and look for a larger structure. We investigate a further similar groups of SA features that are geometrically similar, forming active lobes in the activation space. So this is kind of the animal brains, which have functional groups, a well-known 3D space. So these are the speech production, the audio cortex production, and then also the sort of amygdala for processing emotions. Um, yeah, as I said, they define the low partition in the point clouds without positional information, and they're based functionally related to each other. So these would be the vector functions essentially. Yeah, and this is kind of what these kind of brain-like information structures look like. There's lots of different lobes, and some of them overlap, connecting different concepts from what I gather here. Although the spatial structure set, the researchers this paper don't go into the connection of different information structures. It's to do with things like I said, mutual information. However, they just want to point more to the geometric structure of it, and said adjusted mutual information between spatial clusters and functional co-currence-based clusters. This is just tests to show the mutual information of these clusters and how they overlap, but mainly that they kind of group together. And then finally, there's the galaxy scale, large scale point cloud structure. In this structure, the researchers studied the galaxy cells structure. So presumably, this is the LM itself, and mainly over its overall shape and clustering. Yeah, um, they yeah they look at how it studies the galaxy and shapes. Um, so this is kind of what that looks like, and then they do further shape analysis and clustering analysis on this, and then to see how these kind of things group together. So yeah, and then yeah, so that's the paper there. So the main points from it are they kind of group the information structures that have geometric properties.